Hello again and welcome back to Statistics. Today we're in section 5.2, still talking about probability, and today we will cover the addition rule and the complement rule for probability. So we're going to talk about the addition rule for disjoint events, and then we'll talk about the general addition rule, and then we'll talk a little bit about complements. So here we go. Okay, two events are disjoint if they have no outcomes in common. And another name for disjoint events is mutually exclusive events. So let me give you an example of two disjoint events. Consider a bag of 10 chips, like poker chips, that are labeled 0 through 9. Then the sample space for the experiment draw a chip from the bag would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the sample space because those are all the possible outcomes of the experiment. Now suppose event E is choose a number less than 3, and event F is choose a number more than 7. Then the outcomes 0, 1, and 2 would be part of event E, and the outcomes 8 and 9 would be part of event F. And notice that the two events do not share any outcomes. Here is a Venn diagram of the sample space. So the sample space includes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the possible outcomes. But 0, 1, and 2 are in event E, 8 and 9 are in event F, and notice they do not overlap at all because they don't share any outcomes. And so we could say that E and F are disjoint. In other words, they are mutually exclusive. So here is the addition rule for disjoint events. If E and F are disjoint, in other words, mutually exclusive events, then the probability of E or F is equal to the probability of E plus the probability of F. And notice that we are finding the probability of E or F. And also notice that E and F have to be disjoint for this to work. They have to be mutually exclusive. So here is an example for us. This is example 2. It says, suppose that a single card is selected from a standard 52 card deck, such as the one shown. Now a lot of people are familiar with how card decks are arranged, but a lot of people are not. So let me just tell you that in a deck of cards there are 4 suits: spades, hearts, clubs, and diamonds. So the spades and the clubs are both black. The hearts and the diamonds are both red. Every suit contains ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So every suit contains 13 different cards. Now this says compute the probability of the event E equals drawing a king. So let's look at our deck of cards and see how many cards are kings. Well, all 4 of these are kings. So there are 4 kings out of 52 total cards. So we would say the probability of E is 4 kings out of 52 total cards, and that rounds to 0.077. So just to make sure everybody remembers, it's typical to round probabilities to 3 decimal places. That's just what we usually do. So that's what I'll try to do throughout this video. And now let's compute the probability of E or F or G, where E is drawing a king, F is drawing a queen, and G is drawing a jack. Well, we already know that the probability of E is 4 out of 52, and now there are 4 queens as well, so the probability of F is also 4 out of 52. And there are 4 jacks, so the probability of G is 4 out of 52. And now we can say the probability of E or F or G is going to be the probability of E plus the probability of F plus the probability of G. We add all 3 of those together. 4 over 52 plus 4 over 52 plus 4 over 52 is 12 over 52. You really don't have to write that if you're showing your work here. And if you just put it into the calculator like this, the calculator will tell you that that is 0.231. Now, what about computing probabilities for events that are not mutually exclusive? Well, let's go back to our 10 poker chips labeled 0 through 9, and let's let event E be choosing an odd number, and event F will be choosing a number less than or equal to 4. Okay, well, the sample space, again, is all the possibilities. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But the outcomes in E are all the odd numbers. So that's going to be 1, 3, 5, 7, 9. And the outcomes in F are all the numbers less than or equal to 4. So that's going to be 0, 1, 2, 3, 4. Now notice that we do have some overlap here. An outcome of 1 is in both event E and event F, and an outcome of 3 is in both event E and event F. And here's what the Venn diagram looks like this time. Event E contains 1, 3, 5, 7, 9, and event F contains 0, 1, 2, 3, 4, but 1 and 3 are in this overlap area, and then the other outcomes are either in just event E or just event F, or they're not in either one. Okay, so again, E and F are not mutually exclusive because they do share some outcomes. So if we needed to calculate the probability of E or F and we tried to use our addition rule for disjoint events, we would see that the probability would come out a little too high because the 1 and the 3 are in both groups and therefore they would be double counted. It would look like this. Probability of E or F would be the probability of E, which is 5 over 10, plus the probability of F, which is also 5 over 10, but that gives us a sum of 1, and we know the probability of E or F can't be 1 because there are some outcomes that are not in either one. So this probability is a little too high. What we could do to fix it is subtract the probability of 1 or 3 one time. So what we could do is say the probability of E or F would be the probability of E plus the probability of F, but minus the probability of 1 or 3, which would be 2 over 10. So in this case, we would get 8/10, or 0.8, which is right, because if you count the outcomes, you have 1, 2, 3, 4, 5, 6, 7, 8 outcomes in E or F, and 10 total outcomes, so the probability of P or F ought to be 0.8. So this looks right. Let's see if we can get this down in a rule now. So this is going to be called our general addition rule, and it says for any two events E and F, the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. Now this is called the general addition rule because it works on both mutually exclusive and non-mutually exclusive events. We saw in the last slide that it certainly is going to work on events that are not mutually exclusive, but it also would work on events that are mutually exclusive because if two events are mutually exclusive, the probability of E and F will be 0 because there won't be any outcomes that are in both E and F. So using the general addition rule on the problem we saw in the last slide, the probability of E or F would be the probability of E plus the probability of F minus the probability of E and F. So minus the 2 over 10, and again that would give us 0.8. Okay, now let's try out our new general addition rule in example 3. This says, suppose a single card is selected from a standard 52 card deck. Compute the probability of E or F if the event E equals drawing a king and the event F equals drawing a diamond. Start by determining whether the events are mutually exclusive. So we'll need to know whether the events are mutually exclusive because if we use the general addition rule, we'll need to know what the probability of E and F is. So the event E is drawing a king, so that's going to be these 4 cards here. And the event F is drawing a diamond, so that's going to be all the cards on the bottom row. Those are all diamonds, and there are 13 of them. And notice that there is one card that is both a king and a diamond. So we're going to need to say that no, the two events are not mutually exclusive since one card is both a diamond and a king. And now let's calculate the probability of E or F. So again, we're going to need the general addition rule here because these are not mutually exclusive. And we're going to say that the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. So now the probability of E is 4 out of 52, and the probability of F is 13 out of 52, and then the probability of E and F is the probability of drawing this one card that is both a king and a diamond, so that's minus 1 out of 52. And then if you put all these in your calculator, you will come up with approximately 0.308. Now I want to make sure that you are doing this the easiest way possible, so you don't really have to go 4 over 52 plus 13 over 52 minus 1 over 52. What you really can do for a shortcut is just say 4 plus 13 minus 1, get your answer there, that would be 16, and then divide that by 52, and it'll give you the same thing with a lot less typing on the calculator. Now in example 4 we have our first look at a contingency table. This is a contingency table, and I'm sure you've seen them online or in textbooks. They're everywhere really. But what we have in this table is 5 different relationship statuses, and we have it broken down by males and females in millions. So you can read the table by rows or by columns or just one cell at a time. For example, we could say the number of married people 15 years or older in the United States is 62.2 plus 62.0 million, and that would be all the married people. Or we could say the number of females in the United States is the sum of all these numbers in millions. Or we could say the number of widowed males is 3.0 million. Or the number of never married females is 34.0 million. So you just have to be careful to read the table and get exactly the data that you're looking for from it. Now I've already added up all of the rows and columns for us, and the total of all the numbers in the table is 242.2. So we'll work parts A through D together here. So the first one says, find the probability that a randomly selected U.S. resident 15 years or older is male. Okay, well the people in this column are the males, so let's go ahead and add up that column. The sum of the people in the male column is 117.8. So the probability that a randomly selected U.S. resident 15 years or older is male is going to be 117.8 over 242.2, which rounds to about 0.486. Now let's look at the probability that a randomly selected U.S. resident 15 or older is widowed. So the widowed are going to be on this third line, and the probability that a randomly selected U.S. resident 15 or older is widowed is going to be the sum of 3.0 plus 11.4 over 242.2. Now you could complete this sum before you write out this fraction, that's up to you, but I just didn't this time because it's only two numbers. So 3.0 plus 11.4 over 242.2, and that comes to approximately 0.059. And again, remember we round our probabilities to 3 decimal places typically. And now let's do the same thing for divorced. So the probability that a randomly selected U.S. resident 15 years or older is divorced is going to be on this fourth line. So that's going to be 10.0 plus 13.8 over 242.2, and that comes to approximately 0.098. Now part D asks us to find the probability that a randomly selected U.S. resident 15 or older is male or widowed. So because we have the or here, we'll have to use our general addition rule. So the males are in this column and the widowed are on this third row. Now what you could do, since you have the table, you could just add up all the numbers, 40.2 plus 62.2 plus 3 plus 10 plus 2.4 plus 11.4, and just make sure you don't count the 3.0 twice. You could do that and then divide that total by 242.2. However, I want us to practice using our general addition rule, so we'll go ahead and use the probabilities that we calculated in parts A and B. And I'm not going to use the rounded values because although it doesn't cause any issues in this particular problem, it can cause an issue. It can cause you to have a rounding error. So instead of using 0.486, which is rounded, I'll use this quotient, which is not rounded. And instead of using 0.059, which has been rounded, I'll use this quotient, which has not been rounded. So let's see. The probability that a randomly selected U.S. resident 15 or older is male or widowed is going to be the probability that he is male, which is 117.8 over 242, plus the probability that he is widowed, which is 14.4 over 242.2, and that 14.4 came from just adding these two numbers together, minus the probability that he is both. So the people that are both are this 3.0 right here, which you'll notice that the 3.0 has been counted in the male number here, and it has also been counted in the widowed number here. So minus 3.0 over 242.2, and that's going to equal approximately 0.533. Okay, now let's talk about complements. Not compliments like, gee, you look nice today, but complement. So notice it's with an E. So it says, suppose the probability of an event E is known, and we would like to determine the probability that E does not occur. This can be accomplished using complements. So this is what it means for an event to be the complement. It says, let S denote the sample space of a probability experiment, and let E denote an event. The complement of E, which we write as E superscript C, is all the outcomes in the sample space S that are not outcomes in the event E. So in other words, E and the complement of E are mutually exclusive by definition. So the probability of E plus the probability of the complement of E always has to be 1. So whatever outcomes are in the sample space that are not in E are going to make up the complement of E. Here's just a little quick example. This says, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? Okay, so the probability that someone has not played is the complement of the probability that they have played. See how I put the little C there to mean complement? So the probability that someone has not played the lottery is the complement of the probability that they have played the lottery. Everybody either has or hasn't played the lottery. Okay, so the complement of a probability is 1 minus that probability, and the probability that they've played the lottery is 0.52. So 1 minus 0.52 is 0.48. The probability that a randomly selected American has not played the lottery is going to be 0.48. And here's example 6, and this says, compute the probability that a randomly selected household earned the following incomes in 2009, and this table has already been totaled up for us here. It says, find the probability that someone made $200,000 or more. Okay, well here is the line for 200,000 or more. So the probability that a randomly selected person made this much or more is going to be 4506 over 117,540. And that is approximately 0.038. Okay, then to find the probability that a randomly selected person made less than 200,000, we could add up all of these numbers. But since we know the total, wouldn't it be easier to say 117,540 minus 4506? So that's using a complement. So we're going to say the probability that a randomly selected person made less than $200,000 is the complement of the probability that they made greater than or equal to $200,000. So that's going to be 1 minus the probability that they made greater than or equal to 200,000, and that is going to be 0.962. Okay, now let's find the probability that somebody made at least $10,000. Well, at least $10,000 means greater than or equal to $10,000. Okay, so again, all of these lines except the first one are representing people that made at least $10,000. So the only line that didn't make at least $10,000 is this first one. So instead of adding all of these numbers together, what we can do is say the probability that somebody made at least $10,000 is the complement of the probability that they made less than $10,000, and then we'll say 1 minus the probability that they made less than $10,000, which is 8570 over 117,540, equals approximately 0.927. Now, I know you're probably saying, if it's easier for me, can I not just add up all of these numbers? And yes, of course you can do that now, but what if this table contained 500 rows? Then it would no longer be worth your time to do it that way. It's better for you to learn this complement shortcut now and learn to take advantage of it while the tables are small, instead of having to get used to it later when it's harder. So spend a little time thinking about the complements. Understanding complements will pay off big for you later on in the course.